Another common application of exponential models are exponential decay models, where we have a substance, usually a radioactive substance, that is decaying over time. And these are often spoken of in terms of half-life. And the half-life of a substance is the amount of time that it takes for that substance to decay to half of its original size. So here are the two formulas that we can use. For a radioactive substance with mass m0, okay, so this is the initial mass, and half-life h, the amount remaining at time t is given by m of t, the mass after time t, equals m0 times 2 to the negative t over h. So h is our half-life. Notice that it's negative because we're decaying. And of course, m0 is our initial mass. Now, if you don't know the half-life, you can look at it in terms of a relative decay rate, in which case we have this formula here, m of t equals m0 times e to the negative rt, and r is that relative growth rate. And it just so happens that that rate, if we do know the half-life, we know that r is always written as natural log of 2 over h, the half-life. And so you can use really either one of these formulas if you know the half-life. It's totally up to you. Generally, the convention is this second one because it uses the natural base E. Polonium-210 has a half-life of 140 days. A sample of this element has a mass of 400 milligrams. Find the mass remaining after 2 years. So I'm going to use the model m of t equals m0, and then I'm going to use the one with the 2 to the negative t over h. And then in part b, I'll use the other one just so we can see it. So m0 is the initial mass, and that's this 400 milligrams. So 400, and then 2 to the negative t over h, which is the half-life, which is 140 days. Okay. Now, it's important to remember what units you're kind of working with. So remember that the masses we're talking about are in milligrams, and the time is in days. So this is our model, and now we'd like to know the mass remaining after 2 years. Now you need to be careful here because this is 2 years, and our time is being measured in days. So we need to know how many days 2 years is. Okay, so there are 365 days per year. So we can multiply that by 2 years to get the total number of days in 2 years. And that gives us 730 days in 2 years. So that's what we're looking for here, is the mass after 730 days. So we go ahead and plug that in. We've got 400 times 2 to the negative 730 over 140. So now we can just plug this into our calculator. We have 400 times 2 raised to the negative 730 over 140. And we hit enter. And we're going to round this to the nearest hundredth, so 10.77. 10.77. And this is a mass, and remember our mass is measured in milligrams. So after 2 years, from the 400 milligrams, we've decayed down to just 10.77 milligrams. For part B, how long will it take for the sample to reach a mass of 80 milligrams? So I'm going to use here, just so we can see the other form, the formula m0 times e to the negative rt, where r is the natural log of 2 over the half-life. So our model is m of t equals the initial, which is 400, times e to the negative, and then r is this thing here, natural log of 2 over the half-life, which was 140 days, and then times t. And now I want to know how long it takes for the sample to reach a mass of 80 milligrams. So that's what we want our output to be. 80 equals 400 e to the negative natural log of 2 over 140t. Now we just need to solve for t. So we can divide both sides by 400, and we have 80 over 400 equals e to the negative natural log of 2 over 140t. 80 over 400 is 1/5, so I've got, or 0.2. So 0.2 equals e to the negative natural log of 2 over 140t. To get rid of this base of e, we do the natural log. So I do the natural log of the left side. I have natural log of 0.2. 0.2. And on the right side, it just gets rid of that base. So I have negative natural log of 2 over 140 times t. And now to get t, I just need to multiply by the reciprocal of this fraction. So, and still negative, so negative 140 over the natural log of 2 times the natural log of 0.2 equals t. So now we're ready to plug this into our calculator. So we've got negative 140 over the natural log of 2, and then that is being multiplied by the natural log of 0.2. And then we can hit enter. We get 325.07. Okay, so 325.07. And this is in days. Our time is being measured in days. Now, you always want to make sure, especially when you've got all this complicated stuff that you're plugging into a calculator, just ask yourself if your answer makes sense, just in the context of the problem. So we have here that our initial mass was 400, and we've jumped down to 80. So if we cut 400 in half once, we get down to 200, and then twice we're down to 100. But then we don't cut it down quite in half again because we just get down to 80 instead of 50. So it should be a little bit more than 2 half-lives, okay? And the half-life is 140, so 2 of that would be 280, and this is a little bit more than that. And so this answer does make sense in the context of the problem.